Hey guys, let's talk kind of dot products and angles. First, let's go back to where we use this in physics, what kind of situation. And one of my favorites is work equals force times distance times cos theta. Now, the reason we have this cos theta is the component of the force in the direction of the displacement is what does the work. Any component of force not in the direction of displacement does no work. So we want to kind of find the projection of force in the direction of displacement. We want to find the component of it in the direction of displacement and then multiply the two things together, the correct component of the force in the direction of displacement. So basically what we're doing is we're finding the length of the force vector, which usually we just use F for, but now we're using components, times the length of the displacement vectors times cos of the angle between them. And we can put this here. If we did F cos theta, that would be the component of F in the direction of the displacement. And then we'd have that component multiplied by the displacement. We'd have our work. By the way, this works both ways. It is also true that if we have the component of the displacement in the direction of the force, this is the component of the displacement in the direction of the force. If we multiply this displacement component, let's say parallel displacement or something, we get the same number. We also get the work. So you can either think of it as the component of the force in the direction of the displacement or the component of the displacement in the direction of the force. That is how we find our work. And this is equivalent to just F dot D. So F dot D gives you the component of one of the vectors in the direction of the other multiplied by the other vector. So just like this, it's equivalent. So it's kind of the projection of one with respect to the other times the other. So this being the projection, the component in the same direction. So any situation in physics where you have a situation like this where you care about only the component in the same direction as another vector and you want to multiply them together, perfect place for dot product. And you can imagine, hey, with dot product, F dot D equals the length of F times the length of D times cos of the angle between them. So we can use this to find cos of the angle if we do the dot product. Though sometimes finding the lengths of force and displacement if we're using the component method is annoying. It's like Pythagoras for each one, or dot product with itself times the square root of it. So here is how we can find the angle. So if you want to find cos theta, it's just the dot product divided by the length of each of the two vectors. But again, finding the length is sometimes a pain in the butt. And if we would just want to find the angle, we can do the inverse cos of both sides and we get that. And keep in mind, it all comes from this idea. Like work is equal to the dot product of force times displacement, but it's also equal to the length of force times the length of displacement times cos theta. And of course, this is not just limited to force times displacement. It works for all vectors, but hopefully you have more of an intuition with this. All right, so here's how you would solve it. It looks delightful, I know. It's not terrible in theory. We want to take the inverse cosine of the dot product of the two vectors together divided by the length of u and the length of v multiplied together. It's just finding the length of u and the length of v is a pain, but anyway, you can just do it. 3 times negative 2 plus 5 times 1 gives us our dot product, and then we can either find the length of this just thinking of it as Pythagoras, 3 square root of 3 squared plus 5 squared, or we can think of it as taking the dot product with itself, so u dot u, and then square root. They're entirely equivalent. Anyway, once you're all done that, you can put it in there and you should get 94.4, I believe, unless I screwed something up. You got exactly the same thing going on here. I've got it all written out for you, so pause the video and figure it out if you're having trouble doing this. Might want to attempt it first on your own. But anyway, here's the answer if you want. Now, once you have that, you can figure out if things are orthogonal. Now, orthogonal is basically the same thing as perpendicular, but there's this null vector that comes up a lot in linear algebra, of which we are kind of doing. Null vector just being the zero vector. And that's considered orthogonal to everything. Anyway. They're not perpendicular to any vector. Yeah, no, they are orthogonal to every vector. Yes, so they're orthogonal, but apparently not considered perpendicular. Anyway, so we want to prove these two things are orthogonal. Fortunately, this is pretty easy because if cos, that would have a 90-degree angle between them, and cos of 90 is just 0. So it's just if the dot product is 0, the two things are orthogonal. Perpendicular, same idea. Anyway, so if we dot product these two, we're like, hey, 3 times -8 plus 2 times 12, that's 0. So they're orthogonal. Fortunately, this is great. Remember, dot product, two vectors. If it's 0, they're orthogonal. And orthogonal is basically the same thing as perpendicular, except the 0 vector is considered orthogonal to all other vectors. All right, if two things are parallel, I'm going to do, basically means that one vector is equal to some constant, positive or negative, times the other. So here we want to prove that 3 comma u is parallel to v. I usually just take the bigger one and divide it by the smaller one. Theoretically, if they are parallel, both the x component divided by the x component and the y component divided by the other y component will give you the same number, and that will be the constant you have to multiply the other vector by to get the bigger vector, or the one you divided the other one by. There. Look at it. Should make sense. There. Negative 6 divided by 3 is -2, and negative 4 divided by 2 is -2. They're equal to the same ratio, so we could just multiply -2 by 3(2) to get v. Therefore, they must be parallel. If you want to prove things are neither, you basically just got to combine these two things. So orthogonal is not terrible. We just dot product it. When we dot product 3(2) and -4, -6, we get -24, which is totally not 0. So it's definitely not, these two vectors aren't orthogonal. They're not kind of perpendicular in space. And then we can do the parallel thing. I just basically took this guy, divided it by that, and this guy divided by that. They are totally not equal, so there's no way they're parallel. If it's not orthogonal, not parallel, it must be neither. And then here are just the answers to these questions. Try and do them on your own, but I figured I'd have the answers there for you. Anyway, thanks for listening, and now you know some university level math. Not that you don't already with the calc, but I do. Nice work.